Hello and welcome! In this video, I'm going to be talking about how to solve inelastic collision problems, and these are perfectly inelastic collision problems that you will find in introductory physics courses. And the problem I have written for us today is three objects hit each other and become one object. The final object has a mass of 100 kilograms, one of the initial objects has a mass of 34 kilograms, and the other two objects have equal mass. The final velocity is 15 I hat plus 8 j hat meters per second, and the first object has a velocity of 30 I hat minus 2 j hat meters per second. We want to find the velocity of the third object pre-collision if the second one is at rest at the time of colliding. Now, these I hats and j hats stuff, if they kind of confuse you, I'll give you a quick rundown. Basically, these are components. This is how you would write a vector in component form. So this is saying that this velocity that we have is a vector that is like this, roughly, and it's some meters per second, that's the unit of the vector, and this is 15 meters per second, and this is 8 meters per second, and those are the components of the overall vector which form a right triangle. This is just a quick way to write down and keep track of components without having to worry about using sine, cosine, tangent stuff. And sometimes you might be asked to write your final answer in this form, and you would do it just the opposite. You would have the magnitude of this guy, and presumably you'd have this angle, and you would just find the lengths or the magnitudes of the two sides, and you'd be golden. And that was the quick little rundown there. Now we're going to get into the actual meat of the problem. So three objects hit each other and become one object. That one object, hello, please, there we go, thank you. This is our massive object, it's 100 kilograms. It is going 15 I hat plus 8 j hat, so if this is 15 I hat, and the reason I'm saying I hat, even though it's written just as a straight I, is when this stuff is written by hand, it has a little caret on top. That is, you can do that on a computer, of course, but usually you can get by with just doing I's and J's. This next, let me finish writing this out. So 8 j hat. This is going this way at some meter per second, which we can calculate pretty easily. All right, so that's all we know about the final object. Now we have one of the initial objects is a 34 kilogram object, and the other two objects have equal mass. The first object has the velocity that we 30 I hat minus 2 j hat, and the second object is at rest according to our question statement. So if I were to just kind of sketch that out, here's why this is so sad. Apparently I draw such bad circles that it doesn't know I'm drawing a circle. Okay, this is object 2. Object 1 is coming at slightly up here, and it's doing this, and this, and this is 30 I hat minus 2 j hat, and the minus 2 means that it's pointing in the negative y direction if you were to think about this within the context of a coordinate system. This guy has a mass of 34 kilograms, and object 2 has equal mass with object 3. If they all add up to be 100 kilograms, and the first object is 34 kilograms, that means the remaining mass that we can use that exists within the context of this problem is 66 kilograms. Now we have two objects that make up this 66 kilograms, and they have equal mass, which means object 2 is 33 kilograms, and object 3 is also 33 kilograms. I'm going to make a complete guess as to where I think this object is going to be. We can kind of we can make an estimate or an educated guess. These two objects, or these three objects collide, and this guy is going to the right and a little up. This is not moving. This one is going to the right and down, but at the end of the collision, they need to be going upward. So I'm going to assume object 3 is somewhere down here because it needs to provide that upward motion with its initial velocity. Now I don't know anything beyond that. Also, I'm going to try and make this the same size as, there we go. We only know that that's the kind of logic that this thing's probably going to do. We don't know the magnitude of that velocity, but we know that it's probably going to be below and to the left of the second object. From here, we can start using some formulas to find our missing velocity. And the formula that we can use for perfectly inelastic collisions is the sum of the initial momentums, not an I hat, just an I, equals the final momentum. Now, momentums can be a little tedious to remember, so this is basically the sum of the initial masses times their respective velocities equals a singular total mass times its final velocity. And we have our total mass and its velocity, and we have three masses, all of known, or we have three objects all of known mass. We know two of those objects' velocities. This guy's velocity is 0 because it's at rest. And now we just have to solve for a missing one. You might be thinking that's a little weird because we don't have any of these actual velocities, we just have a bunch of components. That's actually really handy because this formula works with components, only components. You have to use components whenever you do this formula. If you were to think about these in the context of an XY coordinate plane, you could think that this formula could really be the way you actually use it in practice is the velocities in a singular direction. Okay, so this is why having the components is actually a good thing, because we are not going to use the overall velocities. Like, we don't want to know the velocity of this for the context of our problem. We only care about components. Which means over here, what we are looking for is not this velocity. We are looking for the x component and the y component of this velocity. So from here, we're just going to start plugging and chugging. And by that, I mean we're going to use these two formulas to solve for our unknowns. Now, personal preference, I like to start with the x direction first. There is no concrete reason as to why I like to do that. It's just personal preference. You could start with y, with the y direction, and you would be completely okay. But I like the x, so I'm going to do the x. All right. Let me zoom in here a smidgen. This summation means that we are adding object 1's mass times its velocity in the x direction plus object 2 times its mass in the x direction, times its velocity in the x direction, object 3 its mass times its velocity in the x direction. All of that equals 100 times its mass or its velocity in the x direction. So this is going to be, let me just put it here. And I'm going to write it in black. Actually, no, we're going to continue with our color coding. So object 1, that mass, 34 kilograms, multiplied by its velocity in the x direction. Plus object 2, its mass times its velocity in the x direction. Plus object 3, its velocity times its mass, or wow, sorry, I said that backwards. Its mass times its velocity in the x direction. I'm just going to write an x because that's the number that I labeled this component. We could do Vx if we wanted to get specific. which I think I'm actually going to do. So let me just tack on some V's there. And this concludes our summation in the x direction. All of this equals 100 kilograms times its velocity in the x direction, which is 15. And because we were given components, we don't have to deal with sine, cosine, tangent stuff. We can just use the numbers given. We don't have to actually solve for any of these components. Now from here, we just do some algebra to get Vx by itself. So this is going to be 1500 equals, this is 0, 34 times 30 is 1020 kilogram meters per second, if you are concerned with units. And you probably should be, I'm just not writing them down for the sake of time. So now that I've simplified this ever so slightly, I'm going to do it again. Okay, and now I'm left with this. So if I just divide both sides by 33, our velocity in the x direction for our third object is 480 divided by 33, which is 14.545 meters per second. And I'm going to box this and move on to the y direction, because we have found one of our two unknowns, which means we have to repeat this with our y direction components. And this summation is just like the other one, where it's the sum of our masses times their respective velocities in the y direction equals a singular total mass times its velocity in the y direction. So, object 1, 34 kilograms, times its velocity in the y direction, which is -2. So in my summation, I'm going to write that down. So 34 kilograms times -2 meters per second plus second mass, or second object, times its velocity, which is 33 kilograms. It's still at rest, so this is still 0 meters per second. And then our last number in our summation is our third object times its velocity in the y direction. And we know this is also 33 kilograms times an unknown Vy. And all of this adds up to equal 100, the total mass, kilograms, times its velocity in the y direction, which is 8 meters per second. And just like before, we just do simple algebra to find what our Vy is. So if I were to just run through this math again, we get -68 plus 33 Vy equals 800. So I'm going to add 68 to both sides and get 33 Vy equals 868. Divide both sides by 33. I get Vy for our third object is 26.303 meters per second, which is great. Now we have our two velocities of our unknown third object. And that is what we were asked. What is the velocity of the third object if the second one is at rest at the time of colliding? And we have found that. We have found that the x component of that particular velocity is 14.5 meters per second, and the y component of that velocity is 26.3 meters per second. If I were to write this in component form, just like the velocities we were given, it would just be as straightforward as, let me zoom in between the two here, so you can kind of see where I'm pulling these numbers from. This would be V3 for the third velocity equals 14.545 I hat plus 26.303 j hat meters per second. And that is how you would write this in component form. If you were feeling crazy and you wanted to find the overall magnitude of the velocity, it would just be the square root of I hat squared plus, okay, why'd you change colors on me? Plus j hat squared, which would be the square root of 14.545 squared plus 26.303 squared. And this equals 30.06, we'll do 057 meters per second. And thus concludes our totally inelastic collision problem. There's another video on my channel that is about totally elastic collisions, if you are interested in those. And there will be a explosion problem as well. And as always, if you have any future video ideas or stuff you want me to cover, feel free to leave a comment. And in the meantime, happy learning!